Hello everyone, welcome back to StartPoint. So today we are going to talk about binary search tree. To understand binary search tree, first of all we have to talk about what are trees and what are binary trees. So what is a tree? Tree is a nonlinear data structure that is a collection of nodes with edges to connect them, and these nodes are organized in a hierarchy. So there are three main components in a tree: a root node, and branch nodes and leaf nodes. Leaf nodes are nodes with our child nodes. So now I'll explain each of these components one by one. So root node is the node which starts the tree, and it can be called as a parent since. So here we can see that A has two child, B and C. So it becomes a parent, and this B and C becomes child. And also when two nodes has the same parent, they become sibling nodes. So here we can say that B and C are branch node. We have talked about that, child of A, and B and C are siblings. So now we can call B as a parent since it has two children, D and E. It can be called a parent node, and here C also has a child, so it also become a parent. And now here this A becomes the grandparent. Since children of A has children, this A becomes a grandparent. It's same like a family tree where you have your grandfather and grandmother, then their children like our father and mother, then us. Likewise, in a tree also, we have grandparent, parent and child. So here, what are nodes? Nodes is the place where the data is stored. And here we can see, and edges are the relationship between two nodes. So here the relationship between A and C here, we can call it as edge. And if we talk about the size of a tree, we can get the size of a tree by the maximum length of edges. We can get the size of a tree by the number of edges in the tree. So here we have 1, 2, 3, 4, 5, 6. So the size of the tree becomes 6. And then the other property we have to talk about is depth. Depth is the maximum length of edges, which means that the path with the most amount of edges is the depth of the tree. So here it has equal depth. Here 2 edges and here 2 edges as well. So that's the brief idea of what trees are. Now we're going to talk about binary tree, which means that it can only have 2 children. So here we can see here 11 has 2 children, 6 and 19. Then if we go to 6, it has 4 and 8, 2 children. 19, 17 and 43, 2 children. And here 4 has 5, only 1 child. 8 has 10, 1 child. 17 doesn't have any child. So that's how a binary tree works. So now we'll move to the main topic of the video, binary search tree. Binary search tree is same as a binary tree, but the only difference is the values are arranged in a certain order. So you can see here that the order we are arranging the nodes in a binary search tree is, if we have the root node in the beginning, so the left side of the tree should have a value that are less than the root node value. So if we take 6, then it should have, so if we take 6, the left side of the child should have values like 5, 4, 3, 2, 1, like values that are less than 6. And if we talk about the right side, it should have values that are greater than 6, which means A, 7, 8, 9, 10, 11, like this. So if we take an example here we have, let's take 10. So the left child of the node. So the left child of the root node should have a value that is less than 10. So we'll take 8. And the right child should have a value that is larger than 10. We'll take So now we'll go to the node 8. So here we can take it as a root node for the left subtree. So here also we have to satisfy that left child, root node, right child, principal. Here we can have 5. Here we can have, so now it should be less than 10 since the left child should be less than 10. So we get 7 and here 15, we'll get like 14. Here we will take 2. Likewise, you can draw the tree up to any level you want. So this is the root node, which is 10, root node, and we can see that this left subtree has values that are less than 10, 8, 9, 5, and here it has values that are greater than 10. This is the right subtree. So what you have to understand is that a tree has a left subtree and a right subtree, which is divided by a root, and the values in the left subtree are less than the root node value, and the values in the right subtree is greater than the root node value. That's the simple idea of how binary search tree works. So what are the properties of a binary search tree? No duplicate values, but you can have duplicate values in a binary search tree, but in the standard binary search tree there are no duplicate values. In-order traversal gives the sorted order, and there is a recursive structure. Some of you may not know what traversal is, so we'll talk about what is traversal and what are the types of traversal in a few minutes. So to identify a binary search tree, we have another key point. So here, this is the left child of the left subtree. So it is the least value of the binary search tree. So here you can see it is 5. It is the lowest value, and here 20, it is the highest value of the tree. So what you have to get is that if the binary search tree is done correctly, the leftmost child will be the least value of the tree, and the highest value of the tree will be the highest most child. So here we can see that 5 and 20, this is the highest and this is the lowest value. So if you keep this in your mind, you can easily identify whether this is a binary search tree or another type of tree, and you can easily draw a binary search tree by remembering this key point. So now we'll talk about what are the applications of binary search tree. So searching and sorting, symbol tables in compilers, database indexing, implementing sets and maps. Searching and sorting. So in searching and sorting, it enables fast search operations and returns sorted using in-order traversal. Since the tree is ordered in a particular way, we can easily find a node or a value, or we can delete it easily, and also we can insert a new element easily as well. And for symbol tables in compilers, it is used to store and retrieve variables, function names efficiently during code compilation, improving compiler performance. And for database indexing, database balance binary search trees like AVL and B trees speed up query processing by organizing index data for quick access. And for implementing sets and maps, it supports dynamic structure like tree set and tree map, allowing fast insertion, deletion, and lookups while maintaining sorted order. So now I'll explain how to draw a binary search tree. So here we have an example, values 5, 10, 4, 2, 16, 7, 1, 20, 15, 3. So we start with the first value 5, it is our root node. Then we have 10. So if you remember the principle I have told before, left child should be less than the root node, right child should be greater than root node. 10 is greater, here it goes to here, then 4, as we talked earlier, a binary search tree only has 2 children per node. So 5 has, so this level is now finished. So we'll go to the next level, 4. Now we'll start by here by 4. So now we'll go to the 2. So it is less than 4, so it's going to the left side. And we have 16, which is greater than 10, which means that here 5, it checks here, then goes to 10, greater than 10 in the right side. Then we have 7, 5, and so when we are drawing a binary search tree, when we are inserting each value, you have to start from the root node. So here we have 7, starting from here 5, greater than 5, going to here less than 10, so it becomes the left child of 10. Then we have 1, great, less than 5, less than 4, and so it can't go to the right side. 2, like this. Then 20, greater than 5, greater than 10, so this side right child, and 6 in here, it's greater than 16 as well, so it goes to the right child. So now we have 15, greater than 5, greater than 10, greater than 10, and if we go, so we have to go to the right side. Then we have 16, it is less than 16, so it becomes the left child of 16. And for the last value we have 3, less than 5, less than 4, but not less than 2, so it goes to the right side. So we have 3 here, the last value, less than 5, less than 4, so it goes to the left child. We have 2, 3 is greater than 2, so it goes to the right side here. So this is simply how we can draw a binary search tree. I hope you understood how to draw a binary search tree. So we'll take another example. So here we have 8, 1, 2, 14, 12, 9, 21, 6, 10, 4. So we'll start from here, 8, the first value, then 1 goes to this side since it's less than 8. So 2, it is greater than 1, so it goes to the right side and it becomes the right child of 1, 2, then 14, it goes to here, 12, greater than 8, less than 14. Here. Then 9, less than. So here it is 8 greater than 9 greater than 8. Here we have 14, but 9 is less than 14, so it goes to 12. And in here also it is less than 12, so it becomes the left child of 12. And here 21, six, less than 8, greater than 1, greater than 2, then it goes to here as a right child of. Then we have 10, greater than 8, less than 14, less than 12. Here it is greater than 9, so it goes to the left child. And then we have 4, the last value, less than 8, greater than 1. Here greater than 2, but if we go to 6, it is less than 6, so it becomes the left child of 6. So now I'll show you how to draw a binary search tree when it has duplicate values. We talked earlier that it can have duplicate values but not in a standard binary search tree. You can draw a binary search tree under 3 conditions. So the first condition is that the repeated value, both repeated values should be to the right of that value, and the second condition is that the both repeated values should be in the left of that value. The third one is by using a counter. So we'll first draw the binary search tree under the condition 1. So here we'll start with 10. So we have 25 goes. Then we have 15 goes to here. 6 less than 10. So now we have 10, which is a duplicate value. So the first condition, as we talked before, it means that the other duplicate value should be in the right of that child. So 10. So we have to go in this side. So 25 less than 25 less than 15. It goes to. Then we have 6 also. Since the duplicate values are going in the right side, here if we take, so here less than 10, 6, we put it in here in the right side. Then we have 2 goes to here. Then next we have 15. So here 10 is greater than 10, less than 25, and here we have the 15, another 15. Since we are storing it in the right side, here we store it. Then we have 12 greater than 10, less than 25, less than 15. Since it's less than, we go to the left child, and greater than 10, it goes to 2. Last we have 18, greater than 10, less than 25, and greater than 15, and here as greater than 15, so goes to this side. So simply what we need to understand is that all the duplicate values are in the right child. All the duplicate values are in the right of that child. So here 10, in the right side and 6 in the right side of the other 6. So now we'll draw it in under the second condition. So we talked about really what is the second condition is. It means that the duplicate values should be in the left of that child. So we'll start drawing 10. Then we have 25 this side, 15, so this is same as what we have discussed before. You just need to draw it under the left child root node, right child principle. Then we have 6. Now we have 10. So it goes to the left child. So 10 greater than 6 goes to the 3. Then we have again have 6. Should go to this side. Now we have 2. Then we have 15, a duplicate value. 10, 25. So 15 should be in the left side of that value. So now we have 12 greater than 10, less than 25, less than 15, less than this 15 as well. So it goes to this side. The last value we have is 18. So less than 25 goes to 15, greater than 15. So this is the binary search tree under second condition. So the last one is we don't draw the, and for the third condition we don't draw the node twice, just add a pointer at the respective value. So this is same as the binary search tree without duplicate values. You just need to add a pointer to each one. So here 25, 10, 25, 15, 6. So now we have another 10. So we put 2 here. Likewise, whenever a duplicate value appears, you have to increase in here. 6. Then we have 2, 15, 12, 18. So I hope you got the idea how to draw a binary search tree under 3 conditions. So now we'll move to the tree. Tree means that we are traversing a tree. There are 3 types of tree traversals: in-order traversal, pre-order traversal, and post-order traversal. In pre-order traversal, we first write the node, root node, and then the left child, and then the right child. And in in-order traversal, we first write the left child, then the root node, and then the right child. And in the post-order, we first write the left child, then the right child, and then at last we write the root node. I'll show you example how traversing is done. So now we have 10, 25, 15, 6, 2, 12, 18. So here we have the binary search tree. So first we'll write it in the pre-order traversal. So as I mentioned before, you must remember that in pre-order we first write the root node, so 10, then we have to go to the left child, which means 6. Now we have to check whether it has any children. So if it has a children, it goes to that child node. So here 10, 6. This becomes the left child, but it has a child of 2. So this becomes another root node, and this becomes 2. So 2, and this is the right node. So then 6. So now we have to check from this subtree. So here we have 6 as the root node, then 2. So now we have to go to the right subtree. We have 25. So now this subtree, and you can also divide into another subtree as well, like this. So 25. So it has a child, so it goes to 15. And since it has and also it has a child as well, but after that 12 is a leaf node, so this is a one side. So 15 is the root node, then 12 left child, no right child, then again goes to 25 since it's the root node of this subtree. Then we have to write the right child 14, and that's the pre-order traversal. Now we will write the in-order traversal. In-order traversal gives us the sorted order. So we have to write, as I mentioned before, in-order means left child, then the root node, and then the right child. So here, if we start from 10, the left child is 6, but 6 has a child, so it goes to the next level, which means 2, and then check whether we check whether the node has a child. So it doesn't have a child, so 2 is our leftmost child. So then we have to write the root node. So root node of this subtree will be 6. So 6, and then we have to check whether it has a right child. So no right child, so it goes to here 10. Then we have to move to the right side. So here 25, starting with 25, it goes down 15. So now we have to check whether 12 has child, node, then left child, then node, and next we have to write the root node of this subtree. So now we have finished this subtree, and from this subtree 25 is the root node, and for the right child 18, and for the post-order traversal, first we write the left child, then the right child of the tree, and then after that the root node. So starting from here 10, it's a root node, then we go to 6, since we have to get the left child, not 6 is not the left child since it has a child. We have to go to 6, but 6 is not the leftmost child since it has a child. So we go to 2. 2 is the leftmost since it is a leaf node. So starting with 2, then we check whether this subtree has a right child. So here we don't have a right child, so we'll put the right node 6. So now since it's left child, right child, and the root node, instead of going to here, we go to this right subtree. So now we'll start with 25. It's a root node since 15 and 18 exist. Then goes to 12, check whether it has to check whether it's the leftmost child. So 12 is the leftmost, and also here in this small subtree it doesn't have a left child, so 15. Then for this subtree we have a right child, so 18. Then after that we are going to enter 25 since it's the root node, and lastly we are going to add 10 since it's the root node of this entire. So here these are the three main types of traversals. You got idea of what tree traversal is and what are the types of trees available, and how to write tree equation using those traversals. So now what we have to do is the implementation of a binary search tree. So let's try to implement a binary search tree. So first of all we'll try to implement the insert operation. So let's take a binary search tree like this. We have 15 as the root node, then we have 8 as the left child of the root node, 24 as the right child, and then 8 has 5 and 11 as children, and 24 has 9. So imagine that we have to insert 12 to the search tree. So what we do is that we start from here. Whenever you are inserting an element to the binary search tree, you have to start from the root node. So 15. So now what we have to do is to compare 15 and 12. So we know that 15 is greater than 12. So as the principle of this binary search tree, left child is lesser than the root node and the right child is greater than the root node, it goes to the left subtree. So here, now it's in here. Now we compare it with this root node of this left subtree. So we compare it with this. So we know 8 is less than 12, so it goes to the right child. So it goes to the right side, which means to the right subtree. So now it goes to here. So now we have to compare it with 11. Since 11 is less than 12, which means that it should be the right child of 11. So we can insert the new element to here. So we'll see how to implement it using a code. Let's implement it using a code. So here we have a public class binary search, which is a class, and we are going to create a static class name node to get the left child and right child of that node. So we are going to create a constructor to initialize the objects. Then we need to create a root, which means it's the top node where the binary search tree starts. So now we'll here the public void insert. This public method will call the insert recursive function where we are implementing the insert operation. So we'll start from here. Public node insert recursive node and current. So here we are passing the parameters current node and the value we are passing when inserting a new element. So here if current equals null, which means that if the current node is null, which means the root node is null, we are going to insert the new element to the current. And if here in the next if condition value is greater than value dot current, which means that the value we are entering is less than the current value. So as we know, the lesser values are in the left child. So here current left, we need to enter this new element as the left child of this current value. So as current dot left insert recursive, so we are going to call again the insert recursive method, and for now as the parameter current, we are going to change it to the current left, since we are now in the current left, and value will be the user input value. So when we call this function, here it replaces with the current left and value. So when we go to here, it will insert the element at the left child. So next we have else if. When the value is greater than the current value, we are gonna insert it in the right child. So here it's same as the before one. Current dot right, insert recursive, parameter gonna replace with current dot right, since now we are in the current right, and the value. So after that it will return the current, which means when it's here it will return the current, here it will return current left, and here it will return current right. Next I'll explain how to do the find operation. So it is same as the insert. We need to do is to find a value that the user has input. So same as before, like insert, we have to do the comparison. So here let's take 19, we need to find 90. It checks here whether 15 is greater than or lesser than 90. So it's 90, so we go to the right side, since the values that are greater than 15 are in the right subtree. So here 24, and check whether it is greater or less than 24. So 19 is lesser than 24, so we go to the left side. So here we have 90. That's how we find element in a binary search tree. So I'll show you it in the code. So here we have a public method called search element, where we enter the value we need to search, and here we return search helper root value. So here we are passing two parameters, the value current node and the value of it. So we are passing the current node and the value the user has input. So the search helper has parameters node current, where we create an object using the node class, and the value. If current equals null, returns false. So when it's starting from the top node, so here current node null means current is the top node where the binary search tree starts. So which means that if the current is null, which means that there is no top node, that means there is no binary search tree. So as we know, to have a binary search tree, we need to have a top node, which means the root. So if this root is null, then there is no binary search tree. So it will give us a false, because there is no elements. And then we go to the value. So value equals to current dot value, which means that we are checking whether the value of the current node we are in is equal to the value that the user input. So here if it is equal, it will return true. Then again it goes to if the value dot current. So here it checks whether the current value, the value we are currently in, which means the node we are currently in, top root node, check whether the value is greater than or lesser than. So here it checks whether it's lesser than the current value. So again it calls the search helper function recursively. So here, since now we are in the current left, so see, as we know the values lesser are going into the left side, so it will pass the parameter as current left, because we need to search it in the left subtree. So it will pass current left and then the value. Likewise it will recursively call until the value is found. And then here if it is, and here if the value is higher than the current value, it will call the search helper with the current dot right, because the values that are greater than the current value are in the right side of the tree. So here it passes current dot right, so it will search the value in the right side of the tree. So it will also recursively calls until the value is found. So that's how the search helper operation is done. Now we'll move to the remove operation. As for remove operation, there can be three conditions where the element we are going to remove can be a leaf child, it can be a node with one child, and it can be a node with two children. So process of deleting the value according to these conditions will be different from each other. So first, so if I get a leaf node, which means there are no child, yes, let's take 11. So we need to, so first of all, before removing, what we have to do is to find that 11. How to find 11? As we have discussed before, search operation, first we need to compare it with from the root node 11 or 15 lesser, so goes to the left side, and compare it with this 8 greater than 8. So here we have found 11. So this is a child, so this is a node without child, so you can easily delete it. Now we'll say we have to delete 24 where it has one child. So what we have to do is, we'll check, we have to first find the 24. We check here, 24 greater than 15, so it goes to the right side. So here we have 24. So what we have to do is that we have to replace the value of this current node with the child of that current node. So 19, we're gonna add 19, and we just need to remove this one. If we need to delete a node with two children, let's say 8, so 5 and 11 we have. So again we have to compare, 8 is smaller than 15, so goes to the left side of the tree, and here we have 8. So this is little harder. So here 8. So what we have to do is to find the minimum value in the right subtree. So here we have only 2 children, there are no other levels, so only 11 is there. So what we have to do is, we have to replace the current node with the smallest value of the right subtree. So which means we have to replace it with 11, and we can remove this. I hope you got the idea how the deletion is done. So I'll show you how it is done in the code. So here we have a static class named delete results. Create an object using a node, and here we have a flag to detect whether the value is deleted or not, and here a constructor to initialize the objects, and here we have public void delete where it recursively calls the delete recursive function, and here root results not, this is to update the root of the tree, and here if the result dot is deleted, it will print a message saying delete, it was deleted, and if it isn't, if the flag returns with the false, it will print a message saying it was not in the tree. So here we have the delete result. Here we are creating the delete recursive method using the delete result class, where we are passing the parameters node.current and the value the user is entering. So if current, which means, as I mentioned before, if the current node, which means the top node, since the binary search tree starts from a root node, so it is, if it is null, it will give us false, since it means that there are no values in the binary search tree. So here if the value is less than the current value, which means which means that the current value, which means that the value in the root, if it is larger than the value, we are creating an object using delete result class and recursive calling the delete recursive by replacing the by replacing the parameter with current left and value. Since we know that lesser values are in the left subchild, so it passes current left and value. Likewise, it will go by level. So current dot left results dot node, and it will return as the delete result current left results and deleted. It will give whether the current node, it will give whether the value is deleted or not. If the value is greater than the current value, it recurs into the right subtree and update the right child. So here we have delete result, same as in the left side. We replace the parameter with current right and the value, and it will return us with the node that is deleted. And so in this part we are finding the node we need to delete, and after that from this part we are doing the deletion. So current dot left is null. So here we have a condition: if the current left is null and current right is null, which means that there are no child, so it will delete that, it will delete the node without child. See, and here you may have remembered the condition where we need to delete a node with one child. So if the child is on the right side, which means that current dot left, we are checking it by using this condition. If the current dot left is null, which means there is no child in left side, it will return the current right. It will return the node in current right, and the flag will give us true. So it will delete the child in the right. The node has a child in left side, which means current dot right will be null, which means there is no value. It will return the node in current left, and flag will return true. So what will happen when a node has two children? As I mentioned before, we need to find the node with the smallest value in the right subtree. It will done by this function, and so then it assign that minimum value into the current value, and then creates object called right child, delete recursive to. So here by creating an object, we call the delete recursive by passing the current dot right and the minimum value. So it will recursively call that function. So current dot right, which means the minimum values right, will be the, so it will delete the child, it will delete the node with two children. So that's how the delete operation is done. So next we'll go to the display function. So you might remember that I told that in order traversal is the sorted order of the binary search tree. When we need to display the elements in a binary search tree, we need to do it in order traversal. So here we can see that public void in order traversal dot. If the node is not null, which means if it has a value, it again recursively calls in order traversal, which means that if traversal here with the node dot left, which means it goes to the left side of the node and prints the value of that. So again goes to here, and here it replaces the parameter with node left. It recursively calls until the leftmost node is reached. So then print node dot value, then it again print the left ones and then it goes to in-order traversal. Then here it passed the node dot right, which means the right subtree of the tree. So again it goes to here, then we pass the node dot right as the parameter here. Likewise, it also recursively goes until the rightmost child is reached. That's how the display function is done. What we need to remember is that we need to do the in-order traversal to get the sorted order of a binary search tree. So now I'll show you how it's done in a main. So we are creating an object for the binary search tree. Tree is the object, and here we insert 8, 10, 45, 85, 47, 4, 9, 30, 60. So if I show you, so if we draw this binary search tree, 8 goes here. We have done this before. 10 goes here since it's larger than 8. 48, 45, 85, 87, and we have 8 lesser than 8, so here 9 greater than 8 but less than 10, so goes to the left side of 10. 9, then 13 goes here since greater but less, 30, and 80 greater than 8 greater than 10, so goes to right. Here also it is greater than 80, greater than 45, so it goes to 85. Since it's less than 85, goes to here. So if we write the in-order traversal, which means L, R, N, left child, root node, and so here L, N, R, which means left child, node, root node, and then the right child. So we write 4, then the 8, then we go to the right 10, but it has a left child, so 9. So here 10, since this is the next subtree. So now we goes to, if we go here, this is the right child, but if we check from this, it has a child in left, so 30, and goes to the root node, then 80, 60, 85, and 87. So what should be the order is 4, 8, 9, 10, 3, 30, 45, 60, 85, 87. So if we check it here, if we run the code, we can see here here 4, 8, 9, 10, 30, 45, 60, 85, 87. That is what we have got here as well. So then what we have here, we are checking whether it has a element called 7. So here we check whether 10 is there and 5 is there. So we have 10 here, so it should return true. Here it returns. Then we search whether 5 is there. It is not, so it returns false. So then what we have is to delete 10 and 4, and we'll delete So here we can see that when we run the code, we can see that when we call delete 10, it is in the tree, so it will be deleted. Then 4, it is in the tree, and since 5 is not in the tree, it will give us a message that value 5 is not in the tree. So what we're going to do is to call again the display function. So we can see that in the function 8, 9, 13, 45, 60, 85, 87, 10 and 4 has been deleted. So that's how the implementation of insertion, deletion and search of binary search tree is done. So I hope you got the idea what is a binary search tree and what are the applications of it and how to implement it. That's it for today. Stay tuned for the next deep dive. Until then, stay safe.